else. So what are superoscillations? So let me tell you the very first example that came out from a work of Yakira Aronov, who is a major physicist. You may know the Aronov-Bohm effect. He encountered a sequence of functions, fn of x, a, let me put like this, cosine of x over n plus I, a, sine of x over n, all of this power n, where x is our real variable. N, of course, is just an integer, a positive integer, and a is a parameter. So, real parameter. Now, how this appeared is a very complicated story, so I'm not going to talk about that. It comes out of some of his work on weak values. We have a very strong group here at Chapman that does weak values, so the physical implications of these are very well discussed here at Chapman, but I will skip that for the time being. So why is this simple function interesting? It's interesting because you can rewrite it in a different way, right? By using the fact that the cosine of x over n is equal to ei x over n plus e to the minus I x over n over 2. And the sine of x over n, you do the same thing, is e to the I x over n minus e to the minus I x over n over 2i. So when you put these two expressions there, and then you collect factors, you do a little bit of simple stuff, and then you take the nth power, you use the binomial thing, you discover that fn can be written in a different way. Fn of xa can be written as a sum for j from 0 to n of some coefficients, I'm going to explain what they are in a second, e to the I 1 minus 2j over n times x. So what are the Cj and A? These coefficients are the ones that appear when you do the power of the binomial. So Cj and A is going to be nothing but n choose j. And then you have 1 plus A over 2 to the j, and 1 minus A over 2 to the 2j. To the n minus j. N minus j. So what do we see in these coefficients? Well, we see, first of all, that they grow like a to the n, so they become very big very quickly. We also see that they oscillate, plus and minus, because 1 minus a, because of this request, is a negative number. So you have these very highly fluctuating things. And that brings us some interesting consequences. So let me show you what the consequence of this write-up is. So I'm going to delete all of these. This is not a very good eraser, but I have to use the split and clean system. So what is interesting about what we have in front of us? Let's look for a second again at this function. And let's say that n goes to infinity. When n goes to infinity, the cosine of x over n behaves like 1, second order, and the sine of x over n behaves like x over n. So this becomes really, I should say something like this, 1 plus ia x over n to the n, and this eventually gives us e to the iax. Oh, thank you. Right. No, yeah, but when these are even power, then they become positive. It's n minus j. So when it's even, it's positive. Exactly. That's why it kind of. Oh, I'm sorry. No, this depends on x2. X is here, is the exponent. Yeah, this remains a function of x. So what do we see here, and why are they called superoscillation? What we see is that this Fn is a finite sum of exponentials whose frequencies are between -1 and 1. So let me call, for the future that's helpful, let me call this lambda Jn. And we have the lambda Jn are between -1 and 1. So now we have the apparently paradoxical result that you have a finite sum of exponentials with very small frequency, band limited, but they converge when n goes to infinity to something that whose frequency can be as high as you want. Now, the reason why this is possible is because the coefficients Cj depend on n. If you didn't have this dependence, that would be impossible. You cannot construct an exponential arbitrarily large because they're linearly independent. So that's not possible. But because this depends on n, then that allows us to make this happen. But then nevertheless, it gives kind of it's an interesting thing because it shows you can create very high frequency oscillations by starting with very low frequency oscillations. The reason why the physicists are interested in this is because, and this again is something that our university here is pretty much on top of, I would say it's probably the best place in the world for this kind of studies, with the work of John Howell and Andrew Jordan and others working with them. When you want to resolve two objects that are very close to each other, what you need a wave that is able to separate, kind of fit between the two of them. But of course, waves that have this ability when these places are very close are extremely high energy. So for example, if you're trying to do this on cells, the energy is so high that you could damage the cell and you're not able to do it. So what this is telling you is that maybe you can use a clever combination of waves that are, on the other hand, like this. So very low frequency, and you combine them cleverly, and at least in small region and for a small amount of time, you can create the kind of oscillation you want. So this is, 2 weeks ago or a month ago, we had a conference here on super resolution, and there were about 20 people talking about super resolution, and this is one of the instruments for that super resolution. So I say this because there are concrete applications. This is not just pure math, but it's also an interesting mathematical object. So when you look at this, you really have, well, I'm sure mathematicians have millions of questions, but we have 3 important kind of questions that are kind of natural here. And the questions are the following. And I'm going to try to briefly address each one of them. And that's going to be the topic, the talk. So we know what these super oscillations are. So the questions are, first of all, and this is a question that actually was of interest to the physicists, and that's what the very first problem I looked at when we started working on this is, what happens if we take Fn as initial value for Schrödinger equation? So you have a Schrödinger equation, I'm going to write it in a second. You take this Fn as initial value, and so you evolve through time. You take, there is no time here, so you take this as the value for t equals 0. And the question that was of interest to physicists is, okay, so I have this phenomenon which is useful. How long is it going to last when my image is being propagated through the Schrödinger equation in a certain field? So that's a question of great interest to the physicists, and we'll talk about it in a second. By the way, in a few weeks, we should finally have a bust of Schrödinger on campus. We unveiled it, 2 or 3 months ago when we inaugurated the MPP program, and now it's finally been put forward. So next time you come visit, you see, you can have a pilgrimage. We have a Schrödinger, we're going to have Gauss. So 2 valuable pilgrimage sites for us. The second, I'm sorry, we're going to, every bus that we have a little plaque that usually is a famous sentence that somebody said. And so for Schrödinger, we should have put a cat, but I actually put the Schrödinger equation. So you find it there. The second question is, how common are they? So in other words, is this a fairly rare phenomenon, or is something that is actually very ubiquitous and appears kind of everywhere? Right, exactly. So are there other ways to create these? Are there other functions that exhibit this relationship? And finally, 3 is this a special case? of a more general phenomenon. So the first question is a question from the physicist. The third one is a question only for mathematicians, because that's what we like to say. Okay, so this is a good idea. It's an interesting idea, but maybe it's a special case of something much more general. And the second one, I think, is kind of intermediate between the two. So let me say a couple of things about the Schrödinger equation and what we do to try to analyze what's happened, because that's actually going to be the only time that I'm going to make a very veiled reference to category theory, but it's so veiled that it's going to be invisible. You know, the other reason why I prefer the whiteboard or the blackboard to the PowerPoint, because it gives people time to see what's happening versus frantically following. You know, when I give these talks to specialized, like a couple of weeks ago, I spoke at this conference of super resolution, because it was a very technical conference. Then I had the slides, because otherwise I couldn't write everything. But I prefer this way. So the idea is to look at the following Cauchy problem. So the Schrödinger equation is the derivative with respect to t, I in front is equal to minus the second derivative with respect to x, plus you have a potential. This potential depends on the physical situation you're looking at, obviously. So different situation will require you to set different potential. All of these apply to psi. And what we are asking is that when time is 0, we start with our super oscillating function. I think that the little thing that I used to clean now makes it impossible to write. Okay. That's why I'm actually even more traditional. I like blackboards instead of whiteboards. Blackboards, they never go wrong. So generally speaking, to solve this problem is very complicated, because we don't know in general the green function associated to the problem. And that's what you need to construct the solution F. So you need the green function. In some cases you have it, and then you can build the solution. In some other cases we don't, and it becomes very complicated. But even once you have this, the green function, there is still one more important step to do in order to understand whether the phenomenon persists. So what I'm going to do, I'm going to look at only two examples. One that I can actually do in detail, and the other I just have to give you the solution, and you have to believe me. And the first example I want to look is the so-called free particle. So now we take v equal to 0. So I delta psi delta t is equal minus second derivative of psi with respect to x squared. And when t is 0 is a function, the original function. Then you can show that the solution, let me call it psi n because it corresponds to fn of xt, is nothing but the sum of Cj and A e to the ix lambda jn. Remember, lambda jn is 1 minus 2j over n, minus I t lambda jn square. Now, you can see that this is a solution by inspection. You don't need to know anything fancy. You take the derivative with respect to t, and what you get this lambda jn square. You take the derivative twice with respect to x, and that's what you get. So you can just check that this is obviously the solution. And it's also true clearly that when t is 0, you get your original function. So the question is what happens. You know, what we know, forget about the t for a moment, we know is that this expression converges to e to the IAX. That's a super oscillation. But now, is this going to be true also when you have this? So to prove that, in fact, this is true, this is J0 to n, we have to observe the following fact. Psi sanity can actually be written in a slightly different way that the sum from m from 0 to infinity of it power m over m factorial, second derivative, I'm sorry, of order 2m of fn. Now, let me show you why this is the case. Well, essentially, the reason why this is the case is because, let me take the derivative order 2m of fn. I need to rewrite fn here just to make sure we have it in front of us. So fn is simply the sum of the cj e to the I lambda jn x. So when I take the derivative order 2m, what do I get? I'm going to get, let me just do this, a little arrow here. You get I lambda jn power 2m, and then you get the same thing, right? Because the derivative is exponential. But now, I to the 2m is minus 1 to the m. So you can bring it inside there. So now what you have is the sum of what? Of minus I t lambda jn square, all of these over m factorial. And then you have your function, and then the fn. But what is this? This is going to give me exactly this part of the exponent. So what you can show, and it's really nothing but calculus 1, that your psi con n, which we know is that because that's you verify, can actually be written this way. So now we're going to look at what we just wrote, and we're going to make an interesting consideration. So what we proved is that psi n of xt is nothing but some infinite order differential operator applied to your original function. Now, this is already per se an interesting result, right? Because it tells you that the solution to the Cauchy problem for the Schrödinger equation can be obtained as application to the initial value of an infinite order differential operator. The question is this always true? Whenever we have been able to build the green function of V, the answer has always been yes. But it gets increasingly complicated as V gets nastier and nastier. But generally speaking, we can show that in a very large class of examples, it is always true that you can solve this by applying a suitable infinite order differential operator to Fn. So this is the only moment that I can say something about category theory, just to make me feel more at ease here. Infinite order differential operators of this, yeah. Infinite order differential operators, they are objects of something that is this. If O is the sheaf of germs of holomorphic function at the origin, we take the dual, that's what infinite order differential operators are. But this space per se is nothing but the space of hyperfunctions supported in the origin. And when you really want to define hyperfunctions, then you need to, especially in several variables, category theory. So they're then derived category of a certain complicated thing. So this is the only point in which tangentially, that's why I said if you don't say anything, it becomes invisible, but there is some category theory hiding. Okay, so here we have an interesting thing. We have, we solved our thing, but we haven't answered our question. Does this maintain the superoscillating behavior? And the answer is interesting because it's actually non-trivial. And I can show you how easy it would be to prove it, but then I'll show you also why this is not so easy. So I want to study what is the limit for n that goes to infinity of psi n xt. But this is nothing but the limit for n going to infinity of our differential operator applied to Fn. And now, if I can switch these two, this becomes P infinity of derivative. So this is my infinite order differential operator applied to the limit of Fn. But the limit of Fn is nothing but e to the IAX. And so you have the result that you are looking for. So you can show that the function, which is the limit of the sequence, which is the solution to this problem, converges. So what you're going to have that you're going to have e to the I a x minus I a t squared. So that's going to be the limit. And so you have the super oscillatory phenomenon remains true when you look at this case. So the reason why I say this is a very easy proof, but the part that is not easy is this exchange here. How can you show that you can interchange the sign of limit with the sign of the infinitorial differential operator? To show that you can do this requires topological vector spaces, locally convex topological vector spaces. So you have to look at, so this is Grothendieck style kind of stuff, but before his more advanced things. So you have to look at the spaces in which these functions are, and then you have to show that these operators act continuously in that space, and so then you can shift the limit. So it's a kind of a very nice, neat success. So in the particular case I just showed you, the operator is this one here. IT to the m over m factorial derivative to m with respect to x. Because that's the case of v equals 0. When v is not 0, you have much more complicated operators. But they all belong in the same class. So they all belong to, and the class can be described by looking at this function. These functions are very special because these are real analytic functions, right? They are finite sum of exponential. So because they're analytic, they expand to holomorphic function, but in fact, they expand to functions which are entire. Not every real analytic function is entire, but they are. So these are very special space for which, fortunately, we understand the topology super well. More than that, they are restriction of holomorphic of entire function, but also with certain growth conditions. So they don't grow faster, for example, the e to the z square. And so then we know exactly what is the class of infinitorial differential operators that act on those spaces. So there is, in this little line, there is really a lot of stuff that is hidden. But I think the idea, the central idea is clear. You have to prove that this operator is continuous. The story that I always tell when I am at this point in this talk is when we send the first paper on this topic to the publisher, the paper was accepted, but the referee was very annoyed that we took so much time to show him that we could exchange these two things. But among mathematicians, we know that you can't exchange the limit when you have a double limit. So, no, he was a physicist. We eventually end up knowing who he is because he made this comment to us in person. But now he finally, right. Exactly. So I think that the thing that to me was interesting at the time is that from the point of view of the physicists, they knew that this result was true. They knew it because for them, everything that I'm writing here is actually particles doing certain kind of stuff. So in their mind, it was kind of obvious, if you want to use the word. But when you need to show rigorous, that becomes a little deeper. But now, every time this guy writes a paper, he always talks about how complex and sophisticated the issue of the limit is and makes reference to that paper. So I think we are in good shape. We love each other. Okay, so next, yes. Yeah, well, so most of these, I showed you how to build the solution here because it's such a simple example directly, but generally speaking, you would use Fourier transform to do that. So now let me tackle very briefly the second point, and then I'm gonna go back to Schrödinger to justify the third question, which is this a special case or something more general? So the second point is that actually we proved a very neat and simple result, because one could say, for example, okay, so we understand how this is working, but this is a very kind of peculiar example you picked up. You take this really kind of fancy function, and then you do this little trick, and you get the super oscillatory phenomenon. But for example, and the reason why question is a good question is because for many, many years, this was the only example that every paper on super oscillation would start with. So there was like nobody, not other real discussion on this. But the question, we have this lambda Jn, which is 1 minus 2j over n. Are they important? I mean, is it important they have to be this number, or could there be other numbers? Well, it turns out that it doesn't matter. So you can take any sequence lambda Jn. And when I made sequence, that means n goes from 1 to infinity, and j goes from 0 to n. And then you can show that you can write e to the I ax, for example, as a sum of some new other number, let me call it dj and a, e to the I lambda j n x, where these dj now are defined as the product of lambda jn minus a over lambda kn minus lambda jn, with k that goes from 0 to n and k is different from j. So this is nothing but Lagrange interpolation. Yes? I'm sorry? Yeah, always between -1 and 1. Thank you. I mean, actually, it's true no matter what, but then it's not interesting. You know. The lambda were the exponents in the Fn. So this super oscillating function is a sum of some exponent with small frequencies. And these were the 1 minus 2j over n. And this number comes out when you do the binomial formula. Right. Exactly. So the question is, what if I take another sequence? Still between -1 and 1, but now you pick the points arbitrarily. They don't have to be with this one. Well, you can use Lagrange interpolation. You can show this function still has the same phenomenon. No, now the new function is this one here. So it's still, well, no, it's still, because it's still a sum of exponential with very small frequencies. And you show that it's still this converges to e to the IAX with a arbitrary large. Exactly. So it's the same phenomenon, but now this is originated without using that very particular function. So you can take any. So this leads us actually to a slightly different consideration of what we think about super oscillating functions. So, and that will lead us eventually in understanding which way I think this is a special case and why the special case is important. So let me say again what super oscillation is, and then let me tell you a slightly different way of looking at it. So what do we mean by super oscillation so far? We mean that we can write e to the IAX with a arbitrarily large using only smaller oscillations, or like they like say band limited. So for example, in our example, we show that you can take this lambda Jn between -1 and 1, and you can still write that. That's why we call it super oscillation, because this stuff doesn't oscillate very much, it's band limited, but the result oscillates extremely fast. But there is high frequency, because I can take a arbitrary large. But there is a slightly way of thinking of this that it's interesting. Let's look at the function lower f, let me call it, that associate to a the function e to the IAX as a function from R to R. So now I'm looking at the function whose variable is a, and whose the range of this function is a space of functions. What does this stuff really mean? This stuff says that, well, actually, I'm sorry. Let me write a to the IX. Let me write the example of now. It could be some function fa. So I associate to every value a function of x that depends on a. So in the example we had before, we go from a to e to the iax. So what can I say now about this function f? I can say that the value of f in an arbitrary point of R can be obtained if I know the values of f at infinitely many points near the origin. Notice the change of perspective. Until now, I was talking about oscillation, so I was talking about the exponential. I can construct the exponential with very large frequencies by using very mellow exponential. The original article of Yaki Haronov is how talks about how you can take a box in which you have these infrared rays, and you open the box and a gamma ray comes out. So how can you generate a gamma ray from infrared? That's how you do it, because the infrared are these slow oscillating objects. Now here I forget about oscillation. This FA doesn't have to be an oscillating function. It's nothing to do with exponential. And I noticed that what happened with the exponential here is that it has this interesting property that my value of f everywhere can be determined if I know the value very close to the origin. And so we call this property, we call it Supershift. Which I think is in the title of the talk. So what do we mean by Supershift? Supershift is any function that enjoys this very peculiar property. The property being that if I know the value near the origin, infinitely many points, then I can determine the value of the function everywhere. So this opens, so I want to give you an example, the first physical example of this phenomenon, because that's interesting. And then I want to tell you a little bit what kind of questions this brings to us. I'm sorry? Countably many, yeah. Arbitrarily. So if I can find points in which it is true, then I say the function admits Supershift. Yeah. It's always between -1 and 1. I think, yeah, near the origin. Notice several things, but maybe the most important is that this is a space of functions. So now we are going from R, let's say, to a space of functions. In fact, these don't have to be necessarily functions. It could be, in some cases, distributions. Or in the example I'm going to give you now, you need to take hyperfunctions. So that's another little touching point with the categories. Because, I'm sorry? Right. So let me show you the example in which we need to take these to be hyperfunctions. And I don't remember the example completely precisely, so, but I know the shape of the function, which is all you need, and then you can find it. So this is the next kind of Schrödinger equation that you want to look at, is the harmonic oscillator. So now you are looking at I delta psi delta t equal minus delta 2 delta x squared plus x squared, all of this times psi of xt. And then again, we are axing psi of x0 is equal to fn of x. So this is kind of the next natural step. So first, the one I solved for you before is the case in which you don't have these, and then the solution is very obvious. Here, the solution is complicated. So I cannot do what I did before for you when showing the infinitary operator. But I can guarantee you that the same approach works there. So you take the green function, you construct the solution to this Cauchy system, Cauchy problem. Then you realize that the solution actually can be obtained by applying a more complicated infinite order differential operator to this. Then you notice that the operator is also continuous on the space of function. You can shift and you get the result. Except that this time you don't have a super oscillation because the function doesn't have exponentials. So in this case, you have a genuine example of Supershift. And the solution to this is not sure. Okay, so this don't use this to solve fundamental problems of physics because it's wrong. There is a little factor here that I don't remember of t, and then here you have something like minus I over 2 x squared plus lambda jn squared times the tangent of t plus I lambda jn x over the cosine of t. Okay, so this is very, very close to the right solution. I think actually it's the right solution if I would remember what h of t is. So this turns out to be the solution to this problem. Now, when you play the game, as I said before, now you can show that this can be obtained by applying a suitable infinitary differential operator to this. You show that there is continuity, and so this is going to converge, at the end of the day, converge to the same h of t, whatever that is. And then now here you have minus I half x squared plus a squared tangent of t plus I a x over cosine. So you see that you have the same phenomenon, but except that now you don't have a super oscillating situation. Oh, what I forgot, I'm sorry. It is an x. All of this is an exponent. But you don't have e to the I. So the a right now is not anymore the frequency of an exponential. So you couldn't say that this is super oscillation. But what you can say is that I can calculate the value of this function with these a's by simply knowing the value of the function near the origin. So that's what we call supershift. Now, this actually requires hyperfunction because, in fact, this solution obviously has the singularities. These are essential singularities. Now, when you have distribution are polar singularities arise. These are essential. So this actually, this convergence is in the space of hyperfunctions. So it becomes a little more complicated. But the philosophy is the same. So the technology can be differing, the kind of arguments, but the philosophy of the proof is exactly the same. So now we have that we started by looking simply e to the I ax. We noticed that that develops well. We noticed that we can extend it and continue, but now we have a phenomenon that is not super oscillatory in that strict sense, but still maintains this property that is very peculiar, right? That you can find the value of the function everywhere by just knowing near the origin. So now what I want to close with is by describing what is the natural question that arises from this, and which has been my work for the last 3 to 5 years with a group of colleagues from Milano, Irene Sabadini and Fabrizio Colombo, and from Bordeaux, Alain Iget. So this is a group, and we've been working very intensely on this. So let me tell you what the question is, and I'll give you a very preliminary answer. Yeah. Okay, so that's, I'll tell you something about periodic in 1 second. So let me, for completeness, let me write the name of the co-authors on this. Sabadini, Colombo, and Iget. So when we look at this definition, there is something that should strike us as interesting. When you have a function f that is analytic, what does it mean to be analytic? It means that I can calculate the value of f of a as long as I know f of 0, f prime of 0, f double prime of 0, and so on and so forth. So if I know infinitely many values in the origin, then I can calculate the function everywhere. So this, in a way, is kind of a variation, right? So you don't have infinitely many in the origin, but you have infinitely many values near the origin. So the very first question that we posed is, what is the relationship between these two things? So you'll notice that the technique that I described before really uses the fact for the exponential that the exponential function is the restriction of an entire function. So as it turns out, is that if f is the restriction of some f tilde, which is entire, then f has supershift. Notice that this is more than asking that F is real analytic. That's not quite enough, but if it's a restriction of an entire function, which is a pretty strong property, then it has that supershift property. And it's actually not a very difficult proof to go. So then the question was, can we go backwards? And the converse is not true. The construction of the examples and how you can show this is not true is very complicated, so it really can't fit in this talk. But the converse is not true. So the question that we are debating, that we're working on, is what do I need to ask for these two classes to be the same? So what I have is that these are analytic functions. And these are the functions that have supershift. So there is a gap here. There are functions with supershift that are not analytic. So what I like to solve, and that's actually turned out to be a very, very complicated problem, is I would like to solve the following equation, so to speak. Supershift plus some other property is equal to analytic. This is that we don't have. So what else do you need to be able to prove that something, that forces something here to fall there? So this will give us kind of a different characterization of analytic function. Analytic function is a supershift function that has also this property. And we have a lot of intermediate steps. Periodicity comes into there. If you have a function that can be expressed as a periodic function, then you can show that that's true, but it's not true in general. And this actually, to be honest, I mean, I gave a talk about this a few weeks ago. It's an extremely technical problem. There is a lot of stuff that comes into this that branches out to mostly interpolation. So Bernstein polynomials interpolation is a major tool that we use. Lagrange interpolation. It's really kind of more complicated than we originally thought. Well, I know, but no, I bet there must be some condition. Right. Right. Mm-hmm. Right. No, I understand. Well, because I don't think we really ever need completely, when we do the proof, for example, the analytic implies supershift, you don't really use all the properties of analyticity. And so the question is, we use something, but it's not really the full power, so to speak, of analyticity. So we think that it's possible to find something. And by the way, there are lots of variation of this problem depending on whether the points that you take are what you call a regular spacing or where they're irregularly spaced. So there are a lot of subtleties here. So these last 30 seconds of the talk could be expanded into several weeks of talks. But I think the problem is interesting. The other thing that I want to mention that is connected in a weird way maybe to the concept of these special calculations. There is a very interesting phenomenon that arises here. If you have a phone or anything else, you look up the following thing, and then I'll talk to this. I would need the slide, but the Talbot effect. Can you kindly get it on your phone? You just Google it, Talbot effect. I'm gonna come. Okay, perfect. So you see a very nice picture. It's a black picture with a lot of odd white spots that repeat. That's it, exactly. So let me tell you how is this connected with this stuff that we are talking about. So how do you generate this Talbot effect? This is a very old stuff from the 1800s. It's a typical diffraction pattern. So physicists understand, they're not really very worried about it. So you send, so you have a dark chamber here, and here you make little holes, equally spaced, and then you send a monochromatic ray of light that direction, and then what you see is the effect that the picture that you all have on your phone. Interference pattern, absolutely. Nothing mysterious, so to speak. The question is, where do they intersect? So you can actually model the propagation of the light after this grid by using what is called the Dirac comb. The Dirac comb is simply, and you have a delta at every point in your hole. When you do the development of the Dirac comb, well, you know, because the infinite series of deltas is like an infinite series of exponentials. And these exponentials, you now know that you can approximate it with exponential with very small bandwidth. So you can start seeing that there may be some connection. Well, as it turns out, you can do the calculation, and it turns out that the points where you have the lights on are actually specially connected with the Gauss quadratic formulas. So Gauss, when he proved the principle of quadratic reciprocity, which is going to be on the bust, incidentally, when he proved that, one of these proofs uses this series of exponentials. And we can show, and we showed this in a paper that we published a couple of years ago, that you can calculate that by using superoscillations. So this gives kind of an optical way, if you want. I know it's not what you had in mind when you talked about new calculation technique, but this is the thing that I find fascinating about this picture is that picture is an optical calculation of the Gauss quadratic sums, actually the so-called generalized quadratic sums. So you can look at when they vanish, when they don't vanish, and that's exactly reflecting that picture. So the superoscillation allows you to calculate, if you want, optically, a phenomenon that is really a number theory phenomenon. Yeah, it's the wave function, how it propagates, and interference. And so that's all I wanted to say. Thank you so much for paying attention. Yeah. Yes, sir. Okay. No. What's that?
So thank you so much. So just some clarification. By entire, you mean function that is defined in the complex plane, the whole complex.
Holomorphic everywhere.
The holomorphic.
Yes, correct.
Okay.
Thank you.
And yeah, so yeah, but you are worried only, or you care only about the restriction to the reals.
That's right.
So, but this is not exactly analyticity.
It's more than analyticity. For example, if you have real analytic means that you have a function that can be expressed by the power series, but most important, the analytic definition is that in a neighborhood of every point, it extends as an holomorphic function. So for example, 1 over 1 plus x squared. This is real analytic, okay? Because obviously it can be holomorphic function, but it's not the restriction of an entire function because you have a singularity at I and minus I. So being restriction of entire is actually much stronger. Now, why do we need that? We need that because the limit passage, that is the key passage, uses the special properties of the topology of spaces of function which are entire everywhere. So that's why but you can see here how is that necessary? I'm not really sure that it's necessary. That's an easy way, maybe, for me to prove the thing, because now I have a gigantic theory, topological vector spaces, blah, blah, blah. But maybe that's not necessary.
Yeah, my question for this clarification is that in the equation that you wrote and you want to solve for x, I was wondering if analyticity, if analytic is the correct word.
I see. This one here, this x. Yeah, so first of all, here is the wrong, I should say, restriction of entire. Right, okay, thank you, yeah. I shortened it, but it was crucially, yeah.
Yeah, I just wanted.
Crucial comment, thank you.
Right. Well, thanks for an interesting peek into a completely different area of mathematics that I'm familiar with. You mentioned this very believable example of how you might want to use this super oscillation to maybe study a cell or something. So that's sort of, let's say, man-made super oscillation. Does this kind of phenomenon occur somewhere in nature besides sort of man-made phenomena?
Yeah, well, yeah. I mean, this super oscillation really arose in the work of Yakir when they're trying to calculate the measurement, what they call weak measurement of observables, which it's a very complicated thing. So I'm not going to do justice to it, but let me try. You have you prepare a particle, a system of particles, and then when you evolve them, you know that you don't know what's going to happen. That's the problem with quantum physics. Now, what you do, you take so this T initial, and then you take a T final, and now you take from the evolution of this particle only those that do something that you decide a priori. So, for example, let's say you start with something spin up, you throw them out, and then you pick up only those who maintain that spin. So now you have a subset here. What Yakir has shown is that by using this, now you can kind of move this backwards and this forward, and you can estimate, you can say what was happening midway, which you couldn't do without the final. So he called this a pre-post selected state. When he does that, then you calculate. So now you have what we call the weak measurement of the value, which is actually a quotient in which you have the operator at the initial, final, and then here you have something like this. This value, when you do those calculations, that's when superoscillations appear. So that's how the first time I think Yakir found them. So these were not artificially created, but was a result of this. Now, physicists, there is a very important work of somebody called Michael Berry from Bristol. He has done a lot of work on this superoscillation, how they arise naturally in wave phenomena, acoustic waves. So to your question, they arise on their own. They arise on their own, exactly. Then we use them, mostly John Howell is actually our most experimental guy here, and Andrew Jordan, they use them to obtain this better resolution. But yeah, they arise on their own.
So there's, thank you, Daniele. Beautiful talk. I would say that all of this is related to the uncertainty principle in some ways, right? Mm-hmm. The uncertainty principle, yeah. Yeah, oh yeah. Yeah, so that's, so the second question or quick comment, how, if they are bad functions or functions like, for example, transcendental functions, do they enter into this picture?
Function, most of them are restriction of entire function.
Okay.
So
thank you.
I play my role of philosopher, and I put to all of you a question that I already tried to put during the Grothendieck talk, after your talk in the Grothendieck conference, and I was not satisfied by the answer, not by you, but in general. So if I compare this talk with Drew talks, for example, or with a talk, usual talk in category theory, what Giovanni made when he was here, so a lot of things, I see that there are something very, very, very different. So one difference is that here I do not understand all the details, but I follow the logic. In another, after 3 minutes, I'm completely lost. So, but depend on I begin to learn mathematics as an analyst. So perhaps it depends on me. But I think that is not only a question of depend on me. I think that is really a different style of doing mathematics. Kant said that mathematics has the characteristic of treating the universal in concreto. And I see here the universal in concreto, because you speak of universality, but of something that is universal. You pay all the functions, but you start with a particular function. There's a particular representation that develops in a certain way. You make calculation in a certain way. This calculation gives you. In another sort of mathematics, the universal is the universal. It seems to me that is much more philosophy than mathematics in a certain sense, much closer. So my question is, of course, but then when you say, how can I invert the operator with the limit? You say, okay, in order to explain that, I have to go to the Grothendieck results in terms of spaces made in a certain way. So in some, this philosophical mathematics is necessary to make this concrete mathematics in a certain, concrete and not in the sense that you speak of concrete mathematics, concrete in the sense universal in concreto. So my question is, where is the difference between these two sorts of mathematical? Whether they are two sorts of mathematical, completely I'm wrong. There is the same way of doing it. That is the question. I don't see that we have just a very inside thing. Because, for example, as I pointed out, some things require us to go. So now I wave my hand because I do not think it's not effective at all. But someone who really understands what's going on and you get into how the function is variable, trivial, the function is variable. Styles, but different stages. This is what you. There's no question of styles. It's a question of at which level you stay. So does a mathematics deal with the universal in concreto or deal with the universal in universal? So it's more close to philosophy or is closer to so there is this idea, Kant idea that the universal can be built in concreto. You think that? Yeah.
Yeah, Andre Joyal is an interesting person to think about because most of us in this room would think of it as being highly abstract, right? And yet he writes a treatise about combinatorics from a category theoretic point of view, so very concrete. So I think you're right, Daniele. This is approaching the problems from different perspectives, but I'm not sure it's that useful to think of that as being a distinction in mathematics.
Right. But I think Marco's picking up on a real thing, which is there is a difference in experience between looking at a talk like this and looking at it, even if the complementary and they're part of a unified whole and the end goals are the same. And one distinction I think is that your talk was much more synthetic in nature. It was about sort of axiomatizing some structure, and you sort of nodded to these sort of models of the structure in passing, and they were very important for motivating the work and understanding the work. But the talk itself was conducted at the sort of synthetic level, whereas this talk was conducted on the sort of analytic, and not in the sense of complex analytic, but just in the sense of being grounded in a model and having that lead the discussion, the sort of narrative thread of the talk. So I think that's a real distinction to make and to be aware of and try and articulate.
Okay, thank you. So thank you, President. Thank you.